Hi, this is Dr. Hay. I'm going to show you how to find the magnetic field near a moving charged particle with velocity v, and you're told where you want to find the magnetic field. So let's say I want to find the magnetic field here at some location, and I'm given the location with distances, and let's say I'm also given the velocity v, which I haven't written down, but it's just some speed v in the negative y direction. So it's given on this grid, on the xy grid. I also know that if x is oriented this way and y is oriented this way, then z must be pointing out of the board. That's an orthogonal coordinate system. I've also drawn a right, something sort of like a right hand down here to get us set up for finding the direction of this B field. Okay, so this is not a, this is not a pointing outwards. This is just a point, a location point. So there's multiple ways you can do this. There's an easy way and a hard way. I am going to show you the easy way, but just so that we're clear, there is another way to do this with a mathematical vector product here. You would, let me just explain that, but I'm not going to do it for you. You would find this unit vector and you would write this in component form as well. So you would be given some v in the negative j hat direction. This v represents some number, you know, like 5 meters per second squared or something. You would need to find this r hat. Now r hat is equal to the vector, which is something with an I hat and a j hat component, and you would need to divide out the length. And the length would be the magnitude of r hat. So for example, if it's 1 centimeter in the x hat direction plus 1 centimeter in the j hat direction, the magnitude of that would be the square root of 1 squared plus 1 squared, which is root 2. So this would be equal to 1 over root 2 I hat plus 1 over root 2 j hat. And then you would do a vector cross product between v and r hat that you have now. And you would be able to find the b direction with a in component form. And you're going to get something that's in the k hat direction. But let me show you the other way to do it. The other way is to use this equation to find the magnitude and the direction with the right-hand rule. Okay, let's tackle the right-hand rule and the direction first. So basically, you're going to get b is equal to some magnitude and some direction. Let's find the direction with the right-hand rule. So do this with me. Point your right hand downward, so it's kind of like curling around your whatever notebook surface you're working on. Your right fingers are pointing downward. That's your index finger and your middle finger and all the rest. They're pointing downward, and your thumb is kind of pointing at you. Your thumb is straight out away from this page and towards your eyes. Your fingers are going to curl from the V direction to the R direction. So you're literally closing your fingers like you're gripping your hand around something. So your fingers are going to close. They curl from the V direction to the R hat direction, or the R direction here. So yeah, this little vector represents a unit vector pointed in the same direction as R, but with a length that's just a unit, so unit vector. Okay, so you curl your fingers in that direction, and you see that your thumb is left pointing towards you, if you can kind of visualize that. I'm sorry, this is 2D. I can't really give you a 3D video. So your thumb is pointing at you, and that represents the direction of the B field. That's the B left over. And you see that it's in the same direction as the positive Z axis. So your direction comes from your right-hand rule. That's in the positive Z axis direction, so we're going to have k hat. And the magnitude also comes from this equation. The magnitude we're going to calculate separately. These are all constants, mu naught. You can look that up in the front of the book. 4 pi. Q here would just be given to you. Let's say it was a proton or an electron. You know those charges. You could look that up also. And V is some speed that's given. So here I'm going to do V times 1 times the sine of the angle between those two vectors. So this is a cross product, and there's the length r squared down there. So remember that a cross product, when I calculate the cross product of, for example, two vectors a cross b, that's equal to the magnitude of a, so the length of a, times the length of b, times the sine of the angle between them. This isn't just any theta given in the problem. This has to be the angle between these two vectors here. So here's theta there. Okay, so now I can compute the B field, finding the magnitude and the direction separately. Now to solve this problem, you would have to find a few things. You'd have to find the angle theta here as drawn in the image from the vertical up to that vector, this right here, so that's theta. You would have to find the length of the r vector there. You would have to be given the charge and the speed of the particle, and that's it. Everything else is constant. So that's how you use the Biot-Savart law to find the magnetic field near a moving charged particle. One more thing, I almost forgot. This cross product is not equal to this magnitude. This is a vector up here, and this is not a vector. So I have to be careful when I draw something like that, that the magnitude of this cross product is equal to the magnitude of this. What's missing here is the direction, which I didn't put in there, but did with the right hand rule in our demonstration.